Hey everyone, welcome back to Geospatialize AI. So today we're breaking down one of the absolutely coolest breakthroughs in artificial intelligence, vision transformers. If you do any work in GIS, remote sensing, or even if you just like playing around with satellite imagery, there's a really good chance you've heard this term flying around a lot lately. But what on earth is a vision transformer? Well, the whole point of this explainer is to totally demystify them for you. We're going to skip the heavy math and just look at exactly how they work, why they're so ridiculously powerful, and how they're basically rewiring the mapping world. Okay, let's dive right into this. Now, you might be wondering, how does AI actually see the whole picture? Historically, this has been a massive bottleneck. For a long time, AI models could really only process data in tiny, isolated little chunks. They literally couldn't see the forest for the trees. But a huge breakthrough happened recently that changed all of that, allowing AI to finally grasp the entire scene at once. And to understand how it does that for our maps and satellite imagery, we actually have to take a super quick detour.
Part 1. Why Transformers Changed AI.
Before we talk about vision, we first need to look at how AI historically learned to read text. Before transformers came along, AI used things called recurrent neural networks, or RNNs, to read language. The problem? They process data sequentially, just one single word at a time, kind of like a slow conveyor belt. Imagine trying to read a whole book through a tiny drinking straw. You see one word, then the next, and honestly, by the time you reach the end of a long paragraph, you've completely forgotten how it started. But then, the transformer architecture dropped, and it threw that conveyor belt completely out the window. It brought in parallel processing. So instead of that straw, it's like just opening the book and looking at the entire page at once. It sees the whole sequence simultaneously.
Here's where it gets really interesting. Researchers looked at that massive text breakthrough and thought, hey, can we apply this to vision? For years, traditional computer vision relied on convolutional neural networks, or CNNs. Those basically use localized filters to scan tiny sections of an image, like dragging a little magnifying glass over the pixels. But the creators of the vision transformer, or ViT, proved we can ditch those specialized filters entirely. We can literally just treat images exactly like text sentences and, amazingly, get even better results. So how does looking at a whole image at once actually work in practice?
Which brings us to Part 2. How attention works.
Okay, so transformers use this brilliant mathematical system called self-attention to figure out what's important. It relies on three main parts: a query, a key, and a value. Let's use a quick satellite search analogy to make this a bit more tangible. The query is what you're looking for. Let's say the AI is asking, hey, where's the road? The key is like a little label on different parts of the photo replying back, oh, this section over here contains a road. And finally, the value is the actual raw pixel content of that specific section. The model is constantly running these queries against the keys to pull out the most valuable visual info.
But wait, it doesn't just do this once. Transformers use what's called multi-head attention. This means the model uses multiple heads simultaneously to look at the image. I actually love to think of this as a team of, say, 8 to 16 highly trained GIS experts all looking at the exact same satellite map. But each expert has a completely different job. One is hunting for sharp building edges, another is scanning for the dark blue gradients of deep water, and another is tracking forest boundaries. They are all doing this at the exact same time and sharing their findings.
And because they're looking at the whole image at once, we achieve global connectivity. See, in older CNN models, a pixel only really talked to its immediate neighbors. If you had a river at the top of your satellite tile and a lake at the very bottom, it took a ton of processing for the AI to realize they were even connected. But with global attention, every single part of the image talks to every other part simultaneously. It instantly understands the relationship between that river and that lake, no matter how far apart they are on the screen. It's a real game changer.
All right, Part 3, turning images into patches.
So how on earth do we feed a 2D map into a 1D model? It all comes down to a super clever 3-step process. Step 1, we take our 2D image and literally chop it up into a grid of square patches, usually about 16 by 16 pixels each. Step 2, we take each one of those little 2D squares and mathematically flatten it out into a long 1D list of numbers. In the biz, this is called linear projection. And step 3, we just treat these flattened mathematical lists as the individual words of our image sequence. Just like that, we've successfully turned a photograph into a sentence.
Now, there is a tiny catch here. Because transformers process that whole open book all at once, they actually have zero idea which patch goes where. If you just hand it a pile of flattened image words, it's totally lost. So we have to add something called position embeddings. You can basically think of these as little mathematical GPS coordinates attached to every single patch. It tells the transformer, hey, this patch belongs in the top left corner, and this one over here goes in the bottom right. It keeps the entire spatial order intact.
Okay, so we have our patches and our GPS coordinates.
But finally, to figure out what the image actually is, the model uses a classification token. We just add one extra blank dummy word to the very start of our patch sequence. As the transformer processes all the data, this dummy word constantly gathers context from every single patch in the image. By the time the processing is done, the final state of this token acts as the ultimate summary of the entire picture. It's the big decider that says, all right, based on everything I've seen globally, this is a picture of a dense urban center, or this is a pine forest.
Moving on to part 4, powerful but extremely data hungry. Look, all this parallel power, it doesn't come for free. We definitely need to talk about the trade-offs because vision transformers are incredibly data-hungry beasts. They are basically a blank slate. They have what engineers call a lack of inductive bias. Remember those older CNN models we talked about? They came with built-in, hard-coded knowledge that pixels right next to each other are usually related. ViTs don't have that at all. They start out knowing absolutely nothing about how images are structured. They have to learn all those spatial relationships completely from scratch just by looking at examples.
And since they start from absolutely scratch, they need an absurd amount of examples to actually get good. Like, if you train a vision transformer on just 1 million images, it'll honestly perform worse than the older traditional models. But there's a magic tipping point, 300 million. When Google trained a vision transformer on their JFT300M dataset, which literally contains 300 million images, the vision transformer suddenly blew past the traditional models and left them completely in the dust.
To put that scaling law into perspective, think of a traditional CNN kind of like a bicycle with training wheels. It's awesome for beginners, it has built-in balance, and it gets off the ground super easily even if you don't have a massive dataset. A vision transformer, on the other hand, that is a high-performance jet. It is way harder to get off the ground, and it requires absolute tons of jet fuel, which in our case is massive amounts of data. But once it finally gets enough fuel, it flies much, much faster and further than that bike ever could.
Which leads us to our final section, Part 5, why this actually matters for GIS.
So how is this jet engine transforming the way we work in GIS? Well, research is showing that vision transformers are practically tailor-made for geospatial AI. ViTs absolutely excel at structured, specialized imagery, which is exactly what satellite and aerial data is. Because they use that global attention to look at everything at once, they're just naturally better at understanding complex geometric layouts compared to older models. And once you have enough data, they scale incredibly efficiently, which is exactly what we need when we're trying to map the Earth at a planetary scale.
And there's another massive win here, memory efficiency. If you work in GIS, you already know handling huge, high-resolution raster files is a total headache. But large vision transformer models can actually handle much larger batch sizes of data than CNNs can under the exact same computing constraints. This means we can process those massive, heavy remote sensing datasets way faster and cheaper than we ever could before.
All right, let's wrap this up with some key takeaways.
We've covered a ton of ground in this explainer today, from reading text to analyzing satellite imagery. Let's do a quick recap. First, remember the open book versus the straw? Transformers process data in parallel, not step by step. Second, they work by chopping an image into a grid of patches and literally treating those patches like words in a sentence, using position embeddings as GPS coordinates. Third, they use multi-headed self-attention to globally connect and find the most important parts of an image instantly. Fourth, they're blank slates. They need massive datasets, like 300 million images massive, to really take off. But when they do, they are unmatched. And finally, that ability to see global context makes them the absolute perfect tool for mapping our world. And honestly, that really illustrates the incredible power of vision transformers. So, before I let you go, I want you to think about something. How could instantly seeing the global context change the mapping or remote sensing projects you are working on right now? Think about it. If you found this explainer helpful in demystifying AI for GIS, please go ahead and hit that like button, subscribe, and follow Geospatialize AI. We've got plenty more clear, beginner-friendly geospatial and AI explainers coming your way very soon. Thanks so much for learning with me today, and I'll see you in the next one.